Hey everyone, and welcome to Airwise Academy, your trusted source for ESA Part 66 learning. Today, we're kicking off Module 2, Physics, one of the most essential building blocks for your journey into aviation maintenance and engineering. Whether you're pursuing a license in Category A, B1 Mechanical, B2 Avionics, or B3 Non-Pressurized Aircraft, this module is part of your foundation. Physics is where you begin to understand the forces, motion, energy, and systems that keep aircraft flying safely and efficiently. So let's get started. Here's a breakdown of the specific subjects we'll delve into within Module 2. We start with Submodule 01, Matter. This covers the fundamental nature of substances, from the atomic structure and chemical compounds to the states of matter, solid, liquid, and gas, and how they change between these states. Next, we move to the most extensive section, Submodule 02, Mechanics. This is divided into several critical areas. Statics deals with forces, moments, and the concepts of stress and strain. Kinetics explores motion, including linear, rotational, periodic, and vibration. Dynamics delves into mass, force, work, energy, momentum, and friction. Finally, fluid dynamics focuses on specific gravity, viscosity, the effects of streamlining, and essential principles like Bernoulli's theorem. Following that, we explore Submodule 03, Thermodynamics. This encompasses temperature scales, various forms of heat transfer, conduction, convection, and radiation, the fundamental laws of thermodynamics, ideal gas laws, and concepts related to engine cycles, refrigerators, heat pumps, and latent heats. Submodule 04, Optics or Light, covers the nature and speed of light, the laws of reflection and refraction, how lenses work, and the application of fiber optics. Finally, Submodule 05, Wave Motion and Sound, investigates mechanical waves, the speed and production of sound, intensity, and phenomena such as the Doppler effect. As you can see, Module 2 provides a comprehensive and essential understanding of physics, directly applicable to your journey in aircraft maintenance. In this video, we'll be diving into the first submodule, an introduction to the basics of matter, atoms, molecules, and states of matter. First, let's break down the three knowledge levels that ESA uses to define the depth of understanding required for each module in Part 66 training. Starting with Level 1, this is your entry-level understanding. At this stage, the technician has general awareness and basic knowledge. They are expected to perform simple procedures, but always under supervision. Think of it like learning the tools of the trade and recognizing parts, but not making decisions yet. Moving on to Level 2, here the trainee is expected to have a deeper understanding. They should be able to explain system functions and understand how components work together. At this level, they can carry out maintenance tasks, but usually with some form of technical guidance or reference to manuals. Finally, we have Level 3, the most advanced level. This is where a trainee becomes highly proficient. At Level 3, the individual should be able to troubleshoot issues, perform detailed inspections, and most importantly, make independent technical decisions. This level is crucial for those who will certify that an aircraft is safe to fly. So, understanding these levels is key, not just for passing the exams, but for knowing what's expected of you at different stages of your aviation engineering career. And here is our first submodule, Matter. Our primary objective in this section is to gain a solid understanding of matter itself. We'll begin by exploring the very nature of matter, delving into what constitutes it, from the basic building blocks like chemical elements to the intricate structure of atoms and how they combine to form molecules. We'll also examine the characteristics and formation of chemical compounds. Following this, we will move on to differentiate between the three fundamental states of matter: solid, liquid, and gaseous. We'll discuss the properties unique to each state. Finally, we'll investigate the fascinating processes of how matter transitions between these states, such as melting, freezing, evaporation, and condensation. This submodule will lay the essential groundwork for understanding more complex physical phenomena in aviation. Before we dive in, please remember that for both B1 and B2 license categories, our focus in this submodule is on achieving a Level 1 understanding. As we mentioned earlier, this means gaining general awareness and basic knowledge sufficient to perform simple tasks under supervision. In this submodule, we will discuss the importance of physics in the field of aviation. Physics is the study of the basic and fundamental nature of matter and energy. It helps us understand how matter and energy behave in relation to physical phenomena. For people who maintain and repair aircraft, a knowledge of basic physics is essential. Physics allows us to explain how engines work, how airplanes and helicopters fly, and countless other things related to aviation and aerospace. In addition to allowing us to explain the operation of things around us, physics also allows us to quantify them. For example, through the use of physics, we can explain what the concept of thrust means for a jet engine and then mathematically calculate the pounds of thrust being created. Matter is fundamental to physics. It's defined as anything that occupies space, has mass, and can be perceived by our senses. Key to understanding matter is the law of conservation, which states that matter cannot be created or destroyed. However, matter can change its physical state, such as from a liquid to a gas. A good example of this is burning gasoline. While the liquid gasoline seems to disappear when it burns, the matter still exists, transformed into gaseous byproducts. It hasn't vanished, it's merely changed form. All matter, whether solid, liquid, or gas, is composed of tiny particles called atoms. Each atom is the smallest unit that retains the unique properties of a specific substance. These unique substances are called elements, and they cannot be broken down into simpler forms without losing their fundamental identity. While elements differ, their atoms share a common structure. At the center of an atom is the nucleus, containing protons which have a positive charge and neutrons which have no charge. Orbiting the nucleus are electrons, which carry a negative charge arranged in specific layers called shells. This diagram illustrates the basic structure of an atom. You can see the nucleus at the center, composed of protons and neutrons, and the electrons orbiting in defined shells. What makes each element unique is the number of protons, neutrons, and electrons in its atoms. Hydrogen, the simplest element, has 1 of each. Oxygen has 8 of each, and copper has 29. This number of subatomic particles defines the element's identity and its inherent properties, and it also influences the mass of the atom. Elements are organized on the periodic table according to their atomic number, which is the number of protons in their nucleus. Each element also has a unique abbreviation. The periodic table groups elements with similar properties in horizontal rows called periods and vertical columns called groups. Here's the periodic table. Notice how elements with similar characteristics are grouped together, providing a visual representation of their relationships. Atoms can bond together to form molecules. When atoms of the same element bond, the molecule retains the properties of that element. However, when atoms of different elements bond, the resulting molecule has entirely new properties. Take water, for example. It's made of hydrogen and oxygen, but its properties are distinct from either of those elements alone. When atoms bond to form molecules, they often share electrons. These electrons organize themselves into layers called shells around the nucleus, and they fill these shells in a specific order. Each electron shell has a maximum capacity. We can calculate this using the formula 2n squared, where n represents the shell number. So, the first shell, closest to the nucleus, n equals 1, can hold a maximum of 2 electrons. The second shell, n equals 2, can hold up to 8 electrons. The third shell, n equals 3, has a maximum capacity of 18 electrons. And the fourth shell, n equals 4, can hold up to 32 electrons. And if we apply the formula, the fifth shell, N equals 5, has a maximum capacity of 50 electrons, calculated as 2 times 5 squared. Now, while shells generally fill from the innermost to the outermost, there's an important nuance. For larger atoms, the fourth shell often begins filling once the third shell contains 8 electrons. This happens because certain energy levels within the fourth shell are actually lower than the remaining available levels in the third shell. The third shell will then continue to fill up to its full 18 electrons after the initial electrons have occupied these lower energy spots in the fourth shell. As you can see in our diagram, this specific sequence ensures electrons occupy the lowest possible energy states, making the atom as stable as possible. The outermost electron shell is called the valence shell. The number of electrons in this shell determines how an atom will bond with others and its electrical conductivity. Atoms with a full valence shell are stable and act as good insulators. Figure 1 highlights noble gases: helium, neon, argon, and krypton. These atoms are incredibly stable because their valence shells are complete. For most atoms, like argon and krypton, stability is achieved with 8 electrons in their valence shell, even if that specific shell could physically hold more electrons. This makes them unreactive and excellent insulators. Conversely, atoms with incomplete valence shells are more reactive, readily bonding with other atoms to fill their shells. These can act as conductors, allowing electrons to move freely. Figure 2 presents metals such as aluminum, copper, silver, and gold. Their valence shells are incomplete, making them highly reactive. These atoms readily bond, and their loosely held valence electrons can move freely, making them excellent conductors. Let's discuss isotopes. Isotopes are atoms of the same element that have a different number of neutrons. This difference in neutron number directly affects their mass. However, isotopes of the same element always have the same atomic number, which means they possess the same number of protons. Because they have the same electronic structure, isotopes behave almost identically chemically. However, isotopes have different physical properties due to their varying masses. Hydrogen, the most abundant element in the universe, provides a clear example of isotopes. It has 3 common isotopes: protium, which is the most common form with just 1 proton and no neutrons; deuterium, which has 1 proton and 1 neutron; and tritium, which has 1 proton and 2 neutrons. Protium and deuterium are stable, while tritium is radioactive. As you can see in the figure, the difference lies in the number of neutrons in the nucleus. Matter exists in 4 primary states: solid, liquid, gas, and plasma. For aviation maintenance, we mainly focus on solids, liquids, and gases. Remember, changing the state doesn't change what the substance is. Water is still H2O, whether it's ice, liquid water, or steam. The key difference between these states lies in how much the atoms and molecules are moving. Solids have the least movement, while gases and plasma have the most. Plasma is a unique state, defined as an ionized gas containing both positive ions and free electrons. It's highly conductive and, because it's easily sustained in stars, it's the most common state of matter in the universe. Finally, matter can transition between states by adding or removing energy, like heating ice to make water. A catalyst is a substance that speeds up a chemical reaction without being permanently changed itself. Think of it as a helper that makes things happen faster. A good example is a 2-part epoxy mix. The main part is the epoxy resin, but when you mix in the second part, the catalyst, it causes the resin to harden much faster. This catalyst becomes part of the final epoxy. On the other hand, we have inhibitors, which do the opposite. They slow down reactions. And that brings us to the end of this session for today. Now, let's warm up with a few questions to review what we've learned. Now, let's get started with question 1. According to the law of conservation of matter, what happens to matter when gasoline is burned? Is it A, it disappears completely, B, it is transformed into a different form, or C, it ceases to exist. Take a moment to think about what we learned. The correct answer is B, it is transformed into a different form. As we mentioned earlier in our discussion, the law of conservation tells us that matter isn't destroyed, it just changes. Burning gasoline transforms it into gaseous byproducts. Question 2. What is the smallest unit that retains the unique properties of a specific substance? A, molecule, B, element, C, atom. The correct answer is C, atom. As we mentioned earlier, each atom is the smallest unit that still holds the character of a specific element. Molecules are formed from atoms bonded together, and elements are a combination of one type of atom. Question 3. Which of the following particles is not found in the nucleus of an atom? A, proton, B, neutron, C, electron. The correct answer here is C, electron. Electrons orbit the nucleus in shells. They are not found inside the nucleus. The nucleus contains the protons, which are positively charged, and neutrons, which have no charge. Question 4. Looking at the simplified element square below from the periodic table, which number represents the number of protons in an atom of oxygen? A, 8, B, 32, C, 15.9994. The correct answer is A, 8. The number on the top is the atomic number, defining the element. The atomic number specifically tells us the number of protons found in the nucleus of that atom. The bottom number is the atomic mass. Question 5. When hydrogen and oxygen atoms bond to form water, what happens to the properties of the resulting molecule? A. The water retains the properties of hydrogen and oxygen. B. The water has properties similar but slightly altered from hydrogen and oxygen. C. Water exhibits entirely new properties different from hydrogen and oxygen. As you may remember from our discussions on chemical bonding, when atoms of different elements combine, something fascinating happens. The resulting molecule can have entirely new properties. The correct answer is C. Water is a great example. Hydrogen and oxygen are both gases at room temperature. Hydrogen is highly flammable and oxygen supports combustion. But when they bond to form water, we get a liquid that is essential for life. Question 6. How many electrons can the first electron shell closest to the nucleus hold? A, 2, B, 8, C, 18. The correct answer is A, 2. The first shell is relatively small and can only accommodate 2 electrons. If you remember, the following shell can take far more. Question 7. Which of the following is true about atoms with a full valence shell? A. They readily bond with other atoms. B. They are stable and act as good insulators. C. They are highly conductive. The correct answer is B. They are stable and act like good insulators. As you remember, atoms with a full valence shell have achieved a stable configuration. They don't need to gain or lose electrons to become stable, making them unreactive. And because the electrons are not readily available to move, they are good insulators. Option A is incorrect because atoms with full valence shells don't want to bond. Option C is also incorrect because their electrons are not free to move and carry a charge. Question 8. Which of the following statements is always true for isotopes of the same element? A. They have the same mass number. B. They have the same number of neutrons. C. They have the same number of protons. The correct answer is C. They have the same number of protons. Remember, the number of protons defines what element something is. Isotopes, by definition, are the same element, just with different numbers of neutrons. Question 9. Plasma is a unique state of matter. What best describes it? A. A gas with no electrical conductivity. B. An ionized gas containing free electrons and positive ions. C. A supercooled solid with high energy. The correct answer is B. An ionized gas containing free electrons and positive ions. As we mentioned, plasma is distinct because it's an ionized gas, meaning it contains charged particles like free electrons and positive ions. This makes it highly conductive, unlike ordinary gases. Stars, including our sun, are made of plasma, which is why it's the most common state of matter in the universe. Question 10. What is the role of a catalyst in a chemical reaction? A. Slows down the reaction. B. Speeds up the reaction. C. Changes permanently during the reaction. As we mentioned in our earlier lesson, a catalyst is a substance that speeds up a chemical reaction without being permanently changed itself. So when we look at our question, the correct answer is B. Speeds up the reaction. Remember, catalysts help reactions happen faster, while inhibitors work in the opposite direction, slowing things down. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to Airwise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning.